Here are the solutions for 3 physics problems from Chapter 12, 17, 21, and 28. Some static equilibrium problems. Number 17, we have a familiar looking situation where we've got a beam supported by a hinge and a cable, like so. And the beam has a weight of 500 newtons. I'm going to go ahead and start making a force diagram for the beam. So that 500 newtons, that's the weight of the beam. That is the gravitational force. And the length is 3 meters. On the left, it's hinged to the wall. On the right, it's supported by a cable. So from the hinge end, we're going to have those two forces that we'll just call Fx and Fy. And let's see, distance d here, don't know what that is, and the least tension that will snap the cable. So there's a tension force here, and we know that the max tension is 1200 newtons. What value of d corresponds to that tension? Well, there's our forces, so let's figure out what the d would have to be. Let me write my equations here. I'm going to start with the net torque equation because I think that might solve all our problems right there. We may have to do further math from there. We may have to set up the net force for the horizontal, net force for the vertical. And do we know, let's see, I guess this distance here, or the angle here, before we get into this, the angle here would be the tangent inverse rise over run. I don't know what that angle is right there. Alright, so the net torque here, if I pick this to be the axis, is 0, because it's not rotating. Therefore, this torque and this torque must be equal. So this torque here would be 500 force times the radius where it acts, that's half the distance, so that would be 1.5 times the sine of the angle that it acts at. It's at 90 degrees. And what's going to be equal to the torque from the cable, which is 1200 newtons of force, times the full 3 meters, that's where it acts. Right, that force is acting at 3 meters, times the sine of the tangent inverse of d over 3. Now, the sine of that angle, I guess there's a couple ways you can think about that. If that looks intimidating and horrible, well, let's go from here and see what happens. So that's 1, so that's 750 is equal to 3600. I think we can do it from here. We'll talk about trig after. So let's see, where's my calculator? So 750 over 3600 is that. Now, if I want to solve that, I want to get rid of this sine, so I have to take the sine inverse of that to get rid of this, right? That's how you undo sine with sine inverse. So the sine inverse of that. So that gets me 12.02 degrees is equal to the tangent inverse of d over 3. And then to undo tangent inverse, I do tangent. So I want the tangent of that angle. It's 0.213. That's d over 3. So d is equal to that times 3. That's about 0.64 meters. So there's the answer for that. You could possibly, there's another way to approach that. If you, I don't think it's particularly going to help though. I guess we could try it and set up this equation. So if you know that this is d and this is 3 meters, then by the Pythagorean theorem, this is the square root of d squared plus 3 squared, right? Which means the sine of this angle is, you could do this, 750 is equal to 3600 times the sine of this angle is opposite over hypotenuse. So you could do that, and then square both sides of that equation and manipulate that, solve for d. You'll get the same thing. So there's another way to approach that. Which way you want to do that, I'm not sure. But to be able to work our way through that one way or the other. Now, part B, that's the answer for part A. Part B asks, to prevent the cable from snapping, should D be increased or decreased from that value? So that's an interesting question. So if we want to prevent the cable from snapping, we would need this to be smaller, right? And how are we going to make this tension smaller? Well, if you think about the balanced forces here, I think that this is easier question to answer if you think about the components here. If we want to prevent this from snapping, we need to have less of a, we can't have any more vertical force. We can have more horizontal, but there's this much here. So what we need to do is we need to we need to increase this angle here, right? If we increase this angle theta here, then we can increase this force and thereby decrease the tension. So we want to increase theta, and increasing theta is going to decrease the tension force here. I feel like that wasn't a very convincing argument, so let me run through that again. So let's say that theta was this is the distance d that's maxed out at this particular angle here. So let's say we increase the distance d. If we increase the distance d, then increasing this value here is going to increase this, which will decrease this. And this does not change, right? I think that's a much better way of thinking about it. Sorry, that first explanation was fairly lame. So if we want to decrease the tension, then increasing d, if we increase the distance d, that will increase the tangent inverse of d over 3, which will increase this quantity and thereby decrease this quantity. So I think that makes more sense. All right, number 21. We have here a kind of similar situation to this sort of thing, but maybe a little bit more complicated here. We've got a strut, a beam here. It's at a 45-degree angle. And we've got something hanging from it here, some mass. There's another cable here attached to it, which is at a 30-degree angle here. And just in the interest of geometry and knowing angles, I'm going to go ahead and fill in the rest of these angles. If this is 45, this is 135, and if this is 30 and 135, it's 165. This is a 15-degree angle right here, and we will need to know that. Right. So I'm going to go ahead and try to make a force diagram for this beam or strut. So let's see. They're not giving us the mass of the strut, so we should be able to do without that. There would be a gravitational force on the strut of magnitude mg, and there will be forces on the strut here, Fx, and here Fy, right? And there's also the tension force here, and there's also this extra gravitational force on the end, which really comes from the tension in this cable, which is, because everything's in equilibrium, equal to 225 G. All right, and they would like to know, oh, they did tell us, I'm sorry, I lied, or I didn't lie, I just didn't see it. The mg here is 45. There's the mass of the strut. I guess we do need to know that, don't we? I missed that for the 45-degree angle there. Okay, so let's set up our net torque equation. The net torque on the strut is 0 because it is in rotational equilibrium. So that means we have two torques, the one from the mass of the strut itself and the one from the mass hanging on the end of it. Those are trying to rotate it one way, and then the tension in the cable is trying to rotate it the other way. And those are in equilibrium. They're tied. So I have 45 G, that's the force, times the radius, which is, they didn't tell me the length of it, so that'd be just L over 2, half the length of the strut, times the sine of the angle between them, which is 45 degrees. Right, it's actually 135 degrees, but we know we can get away with using the supplement because the sines of those angles are equal. Plus, torquing it in the same direction, or trying to make it rotate in the same direction, we have 225 G of force times the radius, that's the full length of the beam, times also the sine of 45. Equal to the torque from the cable here, which is T, that's the force, times L at the full length of the cable, times the sine of 15 degrees. And you can see the L's cancel out here. I don't need to know the length of the cable. So let's see if we can solve that for T. Maybe that's what they want to know, right? That's part A anyway. So part A, let's solve for T. So let's see, that cancels. So T is equal to 45G times the sine of 45 plus 225G times the sine of 45 all over sine of 15. And I'm going to go ahead and factor the G sine 45 out. So I have 45 plus 225, that's 270, times 9.8 times sine of 45 over sine 15. Before I enter there, just going to make sure I'm in degree mode. I am. So that's about 7,230 newtons. That's how much tension there needs to be in that cable there. And then they want to know what are the horizontal and vertical components of the force on the strut from the hinge. So now we need to write our net force equations. What do they want? Horizontal first. So in the horizontal direction, I know that the sum of all those horizontal forces is 0. So what are those horizontal forces? Looks like it's just this and the horizontal component of the tension force. So that means that Fx would be equal to, if this is the 15-degree angle right here, then this here, that's opposite to the 15-degree angle. Oh, wait a minute. That's not a 15-degree angle there, is it? That's 15 and 45 there. So depending on how you want to break this up, I think actually it would be more consistent with the way we do things to do this. Horizontal, vertical. If this is 15, let's see, this is 45, and that's 15, so this is 30 degrees right here. Right? That tension force is 30 degrees below horizontal, because this is 45, this is 15, that's 60, so this would be 30 degrees here. So the horizontal component would be the adjacent to that 30-degree angle, so that would be equal to T times the cosine of 30 degrees. And there's my force there, so there's my T. There's cosine of 30 degrees. So that's about 6,260 newtons. And part C, let's see what we have for our vertical forces. I know that the sum of all the vertical forces is 0 because this is in static equilibrium. So we have Fy up, and then I've got 3 forces down. 1, 2, 3. So that's 45G plus 225G plus the sine component of the T force, the tension force. So that's 270G plus, and T was 7,230 times the sine of 30, which is 1/2. So that's 6,260. Hey, look at that. Those two are equal. That is not any kind of general rule there, of course, that those two would be equal. Those happen to be equal in this particular problem. All right, number 28. So we've got a similar situation to our beam attached to wall, supported by cable here, but this time we've got an extra mass sitting on the beam there. So what do we know? In figure 1243, suppose the length L of the uniform bar is 3 meters and its weight is 200 newtons. Also, let the block's weight, here this block is 300 newtons. And let the angle here be 30 degrees. The wire can withstand a maximum tension of 500 newtons. What's the maximum possible distance x before the wire breaks? Right, so let's make our force diagram of the beam. So let's see what we have. We've got the force of gravity on the beam itself, which would be 200 newtons. And then we have the force of gravity on the beam because there's a block sitting on it. That's 300 newtons. And I don't know that distance. That's just a distance x, right? Unknown. And of course I have my fx and my fy, the components of the hinge force, and then I have the tension here, which is at 30 degrees. I'll call that, actually we're maxing things out here, so I know that that tension force is equal to 500 newtons. All right, so let's write our net torque equation about this axis. It's in static equilibrium, so the net torque is 0, which means if that's my axis, then I have this torque and this torque from those two forces trying to make the beam rotate this away, and then I have this force trying to make the beam rotate this away. So let's write the equation that balances those. I have 300 newtons at a distance of x that I don't know, that's what I'm trying to find, times a sine of 90 degrees, plus I also have the 200 Newton force, the weight of the beam itself, acting at half the length of the bar, which is 1.5 meters. It's also acting at 90 degrees. So you get the full brunt of that torque, or that force rather. And then those are balanced by the tension force, 500 newtons, at the full length of the bar, 3 meters, at an angle of 30 degrees. So 300x, sine of 90 is 1, 200 times 1.5 is 300, sine of 90 is 1, and then sine of 30 is 1/2, so that's 250 times, that's 750. So that all boils down to that, and that means that 300x is equal to 450, which means that x is equal to 1.5. So that means that the maximum distance that that block could be placed is actually right in the middle of the bar. Right? And now, as part A, we are also supposed to find if things are just so as this, then what are the horizontal and vertical components of the force acting on the bar? So same thing that we've done before. Horizontal first, sum of all the horizontal forces is 0 because it's in static equilibrium. So what are those horizontal forces? I have just this and then the horizontal force from the tension here. So that's Fx in this direction, and then this is 30 degrees, so the cosine component here, T cosine 30, which is 250 square roots of 3. And in part C, balancing the vertical components or forces, I have Fy up and the vertical component of the tension, those are up versus these two down. So that would be Fy plus the sine component of the tension force. That'll be 250, right? Equal to 300 plus 200. So if that's 250 there, so the Fy will be 250. And that should do it for those 3 problems.